Hello, and welcome to today's Explainer. I am so incredibly glad you're here. Look, if you've ever stared at a textbook page full of algebra and felt that sudden, familiar spike of math anxiety, I want you to just take a deep breath. We are going to relax today. Think of me as your personal guide, because we're going to take quadratic equations from feeling like this totally overwhelming mystery and turn them into something you can master with absolute confidence. Seriously, by the end of this, it's going to feel completely intuitive.
So, to kick things off, let's look at a real-life puzzle pulled straight from our source material. Picture a rectangular plot of land. It has an area of 528 square meters, and its length is exactly 1 meter more than twice its breadth. Now, how in the world do we find the exact length and breadth? And listen, this isn't just some abstract test question designed to make you pull your hair out. This is a very tangible, physical problem about measuring actual, real-world land. If you were standing in that field right now, how would you solve it?
Well, the answer is quadratic equations. You see, these equations, they're really just a secret mathematical language that we use to solve everyday design and spatial challenges. It's literally the exact same math used to calculate land area, figure out the slope of a massive sports stadium, program algorithms for those shopping discounts we all love, and even route data efficiently straight to your phone. It's just a language, and I promise you, we're going to figure out how to speak this language together.
Okay. Before we even look at a single formula, let's visualize what we're actually doing here. Imagine a smooth, golden-yellow U-shaped curve. In math, we call this a parabola. The standard written formula for this shape is ax squared plus bx plus c equals 0. Now, when a test asks you to, find the roots of an equation, it sounds complicated, right? But all it's asking you to do is find the exact glowing orange spots on this graph where that U-shape crosses the flat 0 line. That's the whole shebang. Finding the roots simply means finding exactly where our curve hits the ground.
All right, so how do we actually find those crossing points? We use this brilliant piece of logic called factorization, or splitting the middle term. And here's the why behind it. A three-piece equation is really hard to pull apart. But if we take that middle piece, the b, and split it into two separate numbers, let's call them p and q, well, our three-piece puzzle just turned into a four-piece puzzle. And a four-piece puzzle can easily be split right down the middle and grouped together. The golden rule here is that your new pieces p and q must add up to b, and they absolutely must multiply together to equal the outer numbers a times c.
Let's actually put this into practice. We're going to pull example 3 directly from the text. This is a nice, straightforward example to build our confidence and see how this new logic works in the real world. Let's break it down step by step.
Okay, we're given the equation 2x squared minus 5x plus 3 equals 0, and we need to find its roots. Step 1, we multiply our a, which is 2, and our c, which is 3, to get 6. Step 2, we need factors of positive 6 that add up to our middle term, which is negative 5. What could those be? Negative 2 and negative 3. Notice how that middle term, the negative 5x, just beautifully splits into negative 2x and negative 3x right there. So now we've got our four pieces. We group them, pull out the common factors, and we are left with two linear factors. 2x minus 3 multiplied by x minus 1 equals 0. This tells us our roots. Those exact spots where the curve hits the 0 line are 3 over 2 and 1.
You are doing fantastic. Seriously. Now, we're going to level up just a bit. Take a look at example 4 from the text. Now, I want to assure you right now, it is completely 100% normal to feel a bit intimidated when fractions suddenly show up in an equation. It's like, oh no, fractions! But take a breath, because there is a super simple, logical trick to make this look familiar again.
So here's our equation. X minus 1 over 3x equals 1 over 6. We need to find the roots. Step 1 is to confidently clear those fractions right out of the way. We can actually multiply the entire equation by the common denominator, which is 6x. When we do that and simplify, look what happens. We reveal a very comfortable standard quadratic equation. 6x squared minus x minus 2 equals 0. Suddenly, we're back in familiar territory. So, multiply 6 and negative 2 to get negative 12. What factors of negative 12 add up to negative 1? Positive 3 and negative 4. We split that middle term, group them up, and our factors reveal our roots are 2 over 3 and negative 1 over 2. See, fractions are absolutely nothing to fear once you know how to sweep them out of the way. All right, it's time for the boss battle. Let's tackle a hard, board exam level word problem. Example 5 gives us a scenario about designing a stadium and asks us to find the exact width of the space for spectators.
Based on the previous section of the text, setting up this real-world scenario gives us the equation 2x squared plus 45x minus 47 equals 0. I know. It looks daunting because the numbers are much larger.
But here's the secret. Just be patient and trust the exact same process we've been using all along. We have 2x squared plus 45x minus 47 equals 0. First, we multiply 2 and negative 47 to get negative 94. Now we need factors of negative 94 that add up to 45. If we just look closely at the numbers themselves, positive 47 and negative 2 perfectly fit the bill. Notice how we split that huge, scary 45x into negative 2x and positive 47x. We group the terms, factor them, and we get x minus 1 times 2x plus 47 equals 0. Our math gives us two possible roots here, x equals 1 or x equals negative 47 over 2.
Let's pause right here, because this is where a lot of smart students lose points on exams. Real talk, let's look at the most common mistakes. The first one is messing up the positive and negative signs when finding your factors. Always double-check your signs. It's such an easy mistake to make. The second mistake, forgetting the real-world context of your math. Look at our equation. It gave us two answers, 1 and negative 47 over 2. But remember, we are measuring the physical width of spectator space. You literally cannot have negative space in a stadium. It doesn't make sense. Therefore, we must logically discard that negative root. The only valid real-world answer is 1 meter.
You have done fantastic work today, and I'm super proud of you. To cement your confidence, here's your quick 5-point cheat sheet. Number 1, the standard form is always ax squared plus bx plus c equals 0. Number 2, the graph is always a U-shape. Number 3, the roots are simply where the curve crosses that 0 line. Number 4, to solve, split the middle term so b equals p plus q. And number 5, always check your product so a times c equals p times q. And, as promised, here is an absolute game changer of a pro trick to solve faster in exams. Don't try to hold all the numbers in your head. Write down all the possible factor pairs of a times c in a vertical list first, and then just scan your list to see which pair sums to b. Honestly, it saves so much mental energy when you're under pressure.
As we wrap up this explainer, I want to leave you with a final thought to chew on. In our last stadium problem, the math flawlessly proved that the spectator space must be exactly 1 meter wide. But think about that for a second. Is a 1 meter width actually enough room for a cheering, energetic, shoulder-to-shoulder crowd? Probably not. The math is perfect, for sure, but the real-world application might need adjusting. If you were the architect, what would you change about the initial variables in that equation to build a bigger, better stadium? Think about it, because you now have the mathematical keys to manipulate these formulas and design reality yourself. Keep questioning, keep practicing, and thank you so much for joining me today.